welcome you again for this course Fundamentals of Compressible Flow. We are in a new module, that is module 4, that is normal shock waves. So, prior to this module we were mainly concentrated on one dimensional flow, and in particular the flow is isentropic. So, we analyzed how we are going to evaluate if a complete flow field is isentropic, and in this isentropic flow field we tried to evaluate all the parameters such as stagnation pressures, static pressures, static temperatures, and all of them are function of the flow velocity or Mach number. So, the next aspect that we are going to decide is the property change in a non-isentropic medium. In fact, when we say isentropic flow, it is a kind of a ideal situations where we want to find out the stagnation conditions from its corresponding static values. So, this stagnation condition could be a pressure, could be temperature, could be density, could be enthalpy. So, for any arbitrary flow field, the stagnation properties are essentially the characteristics when the flow is moved isentropically to rest. So, now moving ahead, if the medium is non-isentropic, what are the possible situations? So, the possible methods to change the flow characteristics in one dimensional compression medium are the formation of a normal shock. So, this is a adiabatic case, but not isentropic. Another way also, in a one dimensional medium we can change the flow properties by adding heat or taking away heat from the system. The third, and this is again since heat is added, so this becomes a, or heat is added or subtracted, then it is also becomes a non adiabatic case. Now, when we introduce a friction in a medium, how do you introduce a friction? We can introduce a length. Length means we can, when a flow is taking place in a one dimensional duct, so we can increase its length or decrease its length. So, that is what we say addition or subtraction of length. Since we are talking about friction, this is also a non isentropic case. So, in all subsequent situations we will analyze all these cases one by one. Now, the first analysis what we are going to discuss in this module is a normal shock situation. So, prior to this study, prior to these lectures, we are aware of the fact that how a sound wave is formed in a medium. So, it is a very small pressure disturbance wave. Now, when these sound waves, these are basically very small pressure waves. Now, when the medium becomes stronger and stronger, how do you do? When we increase the flow velocity or you increase the Mach number. So, that means you are moving towards the supersonic speed. When we are moving towards the supersonic speed at the close to the Mach 1, so that means we are the initiation of supersonic situation. So, we can say that a Mach wave is generated. So, once and when the body moves still at higher velocity, these Mach waves become stronger and stronger. So, we start with this, when these Mach waves become stronger and stronger, we define this as a shock wave. So, this is the basic definition of a shock wave, how it is formed in a medium. So, in this lecture we will discuss about the shock waves, how it is formed in a one dimensional medium, and then moving ahead we will talk about the fundamental equations, that is for normal shock. Why we are saying it is a normal shock? Because this is under these situations we can say this is that medium can be treated to be a one dimensional medium. So, we will talk about those things one by one. Now, let us see what is a shock wave. So physically the shock wave represents the abrupt change in the flow properties such as pressure, temperature, density over a finite thickness comparable with mean free path. So, if you see the mean free path of gas molecules, it is very small, and when we assume that within that amount of thickness, if in a flow field the properties are going to change, then it has to be a shock wave, because these are the instantaneous change. And this shock wave is typically a thin region, and you can visualize is to be about 10 to the power minus 7 meter thickness, and this across this thickness we encounter instantaneous change in the flow properties. So, many mathematicians represent this kind of phenomena of shock wave formation as a discontinuity in the medium. So, a function is discontinuous everywhere, a function is continuous everywhere, but except at a point. So, something of that sorts we say that such a phenomena we can represent as a step, impulse, step or impulse or ramp or hat functions. So, these are the terms that are used by mathematicians to talk about some kind of mathematical background of shock waves. So, what in our philosophy, what does this mean is that, let us look at this figure. So, what you are trying to see that any parameter which is going to change with respect to time. So, this time can be of day, it can be of hour, it can be of second or minute, and what we are looking at? We are looking at this time to be very small as far as the human view is concerned. So, if I talk a time scale of a millisecond or less, so if any event is going to happen in this small instant of time, then obviously there will be, and within this time scale if there are drastic change in a medium, then we view it as a, we call this as a formation of a instantaneous change in the medium. And if you look at any property parameter which is changing with respect to this kind of time step, then we can call this either as a step. So, the step means it is a instantaneous change. By instantaneous change I mean, looking at this figure, let us say I am talking about a 0.2 milliseconds. So, at 0.2 milliseconds the property parameter happens to be 0, but again at maybe very small instantaneous time the property again shoots up to a value of magnitude of 5, but with a very short span of time, and it retains that properties continuously till the end of the event, and in this case let us the event ends at 1 millisecond. So, if this is the case, we call this as a step response. So, instantly property change and it remains with that number 5 as that for 1 second. Now, if I want to close that event at some particular time like 0.8 milliseconds, then that property starting with from that coordinates, that is from 5, it has to come down instantaneously. So, when I say come down instantaneously, this means the way it has risen as a magnitude, at it has come down again to the same 0 value, and again it remains as it is. So, such a function it looks like a hat. So, it is a hat function. Now, let us say that although we are going to that magnitude of 5 instantaneously, but in our case let us allow that to reach that magnitude the phenomena takes certain amount of time. So, that means time means, so we call this as a impulse. So, it is, so for this event we are taking this response as a magnitude. So, it is responding to that event as a slope, that means we reached maybe to the same magnitude of property at of 5, but we take about a time scale from 0.02 to 0.6 millisecond difference, that is 0.4 millisecond to reach that magnitude. Now, again with same way the value drops, that means the number that does not remain at that things that value entire with respect to rest of the time, but rather it falls. So, we call this as the impulse. So, it is like a impulse. Another way of looking at the event is that so the event while rising, it may take at some fashion of rising, like in this case in case that is in the case of ramp. So, we say that we reached with same magnitude parameter of 5, but within a time span of 0.1 milliseconds, but not necessarily that with same time it will fall back, it may immediately fall back, or it may take a bit longer time. So, all these events we call this, with this event, particular event we call this as a ramp. So, likewise the way we define the functions as step, ramp, or impulse or hat. So, typically the phenomena of shock wave events are of this nature, of similar to of this nature. So, in the bottom line we can say that during a shock wave phenomena, the flow property changes instantaneously, and when they change instantaneously, there is a drastic change in the magnitude. So, since there is a drastic range of the magnitude, there is, so entire event that has to happen in a very small milliseconds. So, now with this background, let us see that why that event that phenomena is important to our case. So, now we will talk about something called as super subsonic or supersonic events. So, as we know earlier situations that in a subsonic flow field, the pressure disturbance in the form of sound waves sound wave propagates everywhere in the mediums, and even the body is moving, it is moving in such a manner that it can never overtake the path travelled by the sound wave. So, that is the reason entire information which is about the presence of the body is felt everywhere in the medium. But when you move to the supersonic situations, that means when your body is moving at very high speed, more than speed of sound, then we will land off in a situation that the information will not be shared by the these information about the presence of the body will not be shared into the medium. So, that is what we say that supersonic flow never warns the medium about the presence of the body, because the sound waves can no longer propagate upstream, and because at any point of time the velocity, that is v, is always greater than a. But then if that is the case, then how one has to know about the presence of the body. So, for that situation, see what we say as a characteristics of a supersonic event. So, what we say, if such a situation arises, so nature establishes a phenomena what we call as shock formation process, through which the supersonic flows adjust about the presence of the body. So, this adjustment has to be done in a very small region, and that is nothing but the shock wave. And this hence the shock wave is a mechanism of instantaneous compression of the gas within the thin regions. Why this is a compression? Because the body is moving at a very high speed, all of a sudden this velocity has to be come down to a subsonic value, because this event is only possible, or formation of shock wave is only possible when a body is moving in supersonic speed. And when such a things happens, see this the Mach number of the flow has to be subsonic all of a sudden. When these things happens, entire gas gets squeezed in a very thin regions, that is what the pressure shoots up, and when it is squeezed in the small thin regions, and thereby the entire kinetic energy of the flow gets converted into internal energy, thereby also temperature also rises. So, this event, that means when temperature rises, your T2 will also be greater than T1, if this is the temperature T1 before the shock. So, this is how the event of shock wave that takes in a supersonic medium. So, typical examples in our day to day life, we can say that in a philosophical sense, we can say accident is a kind of situation. If there is an instantaneous accident where there is a large amount of failure, so we can say it is a philosophical aspect of a shock wave. And in fact, in your day to day life, we also say we also create explosion like burning firecracker, okay. And in many aerodynamic facilities, they try to rupture a diaphragm instantaneously, or we can create a detonation waves. So, these are the day to day life, we can create these facilities in the laboratories. And in fact, in coming to the real situations, the motion of missiles and space shuttles normally encounter the shock wave phenomena. So, the shock wave is a very natural occurring event when any body that travels at supersonic speed. So, this is how I have already explained that with respect to these characteristics of shock wave event, it is the instantaneous compression, and with this instantaneous compression, the energy of the energy for the compression is derived through kinetic energy possessed by the upstream of the flow, and this leads to the internal energy increase and temperature increase in the medium. So, again what happens to entropy? So, while flowing through a shock wave, the gas experiences a decrease in its available energy. So, thereby it leads to increase in the entropy. So, it is a non isentropic situations, and the process is phenomena across a shock wave is highly irreversible and non isentropic. Okay. Now, in this type of our lectures, we will our sequence of view will be something like this. So, we can say we can say that this particular shock wave, whenever it generates in a medium, it can be a stationary shock. So, in a stationary shock means I am saying that there is a shock wave sitting in a medium, some flow is entering at some velocity and it is leaving at some velocity. This is how we view by keeping the shock wave as stationary, and this shock wave is moving. So, it is a, we call this as a moving shock. Now, when the shock wave is moving, that means your medium is stationary, but the wave is moving in the medium. So, accordingly we use the terminology like ahead of the shock or before the shock, behind the shock or after the shocks. So, when we say it is a stationary shock, we normally refer what happens before the shock and what happens after the shock. Now, when we say it is a moving shock, when the shock wave is moving and this particular gas is stationary, then we will say that this particular region is behind the shock, because shock has not crossed this region, and this region which is the left and right side of the shock wave, we call this as ahead of the shock, because shock wave has already crossed this region. Okay. So, this is how we do this stationary shock and moving shock. Now, when you say it is a normal shock, so normal shock is a situation where we say it is a one dimensional flow. Why you say that? We can say this shock wave to be one, since it is let us say when you are looking at a stationary shock, that means shock wave is standing in this way. So, what happens in a normal shock, the streamlines that comes are essentially perpendicular to this shock wave. So, that means any point of time the streamlines form 90 degree with respect to shock wave. So, what we can say, we can imagine this to be a duct or imaginary duct, where consisting of large number of streamlines, and all these streamlines are perpendicular to the shock wave. So, we call this as a normal shock, and it is a obviously it is a one dimensional phenomenon. Now, in subsequent analysis we will talk about a oblique shock, which is a two dimensional phenomenon. Now, you can imagine this shock wave can be inclined, like I can say that shock wave may be of, I can incline the shock wave. When the streamline crosses this wave, it tries to deflect. So, such a things we call this as a oblique shock. So, that means when the shock wave is normal to this streamline, it is a normal shock and it is the strongest one. When as and when it becomes inclined, so it becomes a oblique shock. So, it is a two dimensional flow phenomena. So, we will discuss this in the all subsequent lectures. So, now let us see the next topic of this lecture, that is formation of shock wave in one dimensional medium. So, in previous to this I elaborately told that how a sound wave is generated in a medium. So, that point of time we had a very conceptual thermodynamic systems like a piston cylinder device, in which the one side of the cylinder is open. So, we will revisit the same example again, but in a different context. So, in this context what we can say, in the first figure what we see, we can say there is a piston. So, this is the piston and this is the cylinder. It is a long cylinder, but the end is open. So, what we can say, there is a gas in this medium, any gas. So, as and when we say that when we say gas, since the gas is a stagnant situations and is not moving. So, we say its condition as P naught and its velocity is, gas velocity is 0, and all the conditions, let us say its temperature and velocity is 0. Now, what you do is, so it is a now what you do is, we want to give the so you can say this gas may have different layers of gas. You can imagine this gas to be arranged in layers, that is there are infinite layers of the gas, I mean it can be on either side of the piston. Now, what we do is, now in the next event, that is this is the initial situation, then once after that the first initial time the piston of the tube is given a steady velocity, that is with no acceleration, that means towards right. So, what by looking at the steady velocity and no acceleration, what I mean, if I try to plot this velocity of the time plot for the piston, what I can view that initially it is 0. So, I give this stepwise very small magnitude of discrete manner. So, if I want to change the velocity from 0 to certain finite value, then I am looking at this to be happening in very small steps. So, what I do is, I give a very small, and these steps we can say as small dV, and at the second instance I say it becomes twice dV, and third instant it becomes thrice dV, and so on. So, that means now let us say when we are giving the first instant velocity, steady velocity dV to the piston. So, obviously when I give this velocity dV, the piston tries to move at certain velocity. So, as a result, since it is a very small pressure wave disturbance, we can say it will generate a sound wave, or in this case let us put as a compression waves or very weak compression wave, and that is nothing but the pressure wave, and that is generated in the process and it moves a speed a1. So, when I say these things, so since this sound wave has already crossed this medium, this gas has also started moving, which is contained in this region. They started moving with same velocity dV, and when we have the same velocity, then the initial gas situation which is at P 0 and which was the at the initial state, now it has risen to a magnitude dP. Okay. So, with this first wave, the medium gets a pressure disturbance dP. So, this is how the weakest wave that is going to have in the medium. Now, since it is a weakest wave, we call this as a sound wave, that is quite obvious. But with same time instant, if I just increase this magnitude to another dB, and we are looking at the next sequence of events. So, what we do is here the same piston we are looking at another time t is equal to t1. So, that previously that time instant we say it is at t is equal to t0, this is the time instant. Now, what we are looking at this time instant as t is equal to t1. So, here the piston was given the next subsequent in velocity, piston is allowed to move an additional with an additional increment of velocity, so twice dV. So, by this time the first sound wave would have reached at this location, maybe some, and if you look at the pressure versus x diagram, so it would have reached some locations. Beyond that we have velocity of the gas 0 and pressure is P 0. So, in this line we will say this line refers to P 0, and this one the gas has velocity dV and the pressure has P 1, okay. And the second subsequent increment will make this gas velocity to be twice dV. So, this region will becomes will see the next level of pressure increment, and we say the absolute pressure to be P 2. So, what I can say that the jump in pressure from P 0 to P 2 has happened in 2 steps due to 2 step increment in the velocity to the piston. Now same event when you look at different time instant t is equal to t2, obviously we will see that the second wave which is generated here, that is A2, and this A2 will have higher velocity than A1. Why? Because when A2 second wave is generated, that is second wave number 2 and wave number 1, this second wave will have higher velocity, because by the time the first wave has crossed the medium, the temperature would have increased from its T1. So, in other words, what we say that second wave which is generated in the medium, it is moving to a elevated temperature. So, since the speed of the sound is dependent on the temperature, that means A2 is, since A is a function of A is equal to square root of gamma or T, and in the T2 greater than T1. So, we say A2 will be higher than A1. So, in other words, what I am trying to say that, and with when same two waves we are looking at different time instant, we will see that the second wave will come closer to the first wave, because it will try to overtake, and this time, this distance, the entire medium will now become to, we will see this same event, that in a getting squeezed in a small region. Okay. So, we get this P2 gets squeezed in a small region. So, and this is the first wave, this is the second wave, and here this side is B is equal to 0, it is P naught, and this is T1, and this is dV, and this is twice dV. Okay. This is how we see. So, all these things try to, the second wave will try to overtake. So, likewise, every in additional increment of velocity will lead to different sound waves, and all of them will try to move faster than the first wave. So, this essentially means, now we will not use the word sound wave here, because when you say the first wave, it could be a sound wave, but all subsequent waves will not use as a sound wave, we will call this as a pressure wave, because they are not weak. So, all these pressure waves, they moves faster than speed of sound. So, we call this as a pressure wave. And very bottom line is that all these pressure waves, there are as you say that any number of increments, if you say there are infinite number of increments of this velocity, we can say there are infinite number of such pressure waves getting generated in the medium, and every pressure wave will have higher velocity than the first one, and with lapse of time they try to merge in a very small region. So, this is the philosophy that happens. Now, what we see is the when we have the when you view this in velocity increment in very small manner. So, this is how the development of compression waves. So, in this way we call this as compression waves, because we are not using the word sound wave now, except for the first one, which is for sound waves. So, in this way what we say, in fact whatever I discussed so far, if we summarize them, we can say that all subsequent pressure waves through every additional increment of the velocity of the piston would have velocity higher than the previous ones. So, all the subsequent pressure waves through additional increment of the piston would have speeds higher than the previous one. Eventually, all the pressure waves generated at every instance of time are supposed to meet at one point, and the finite increment in the piston of the piston to the right can be imagined to be large number of infinitesimal increments, and this gradual steady gradual change in the velocity of the piston does not accelerate the piston, because it is steady change in the velocity. So, change in the velocity between two successive time step is very small. So, it essentially does not accelerate the piston. Now, the here most important things that happens, that when these waves will try to merge. So, here instead of looking at this event, we are now look at the situation in such a way that we are going to accelerate the piston. So, when I am going to accelerate the piston, so if I plot the velocity and time, so instead of giving this velocity increment in steps, what I am trying to give? I am giving a sharp shoot. In other words, entire steps now becomes a sharp shoot. That means, I squeeze this time t tends to 0, so that I can get the same rise in velocity, but in a very short span of time. So, in this case I will say instead of dV, we will say it is a delta V. So, what I say here, that instead of dV I am giving delta V to the piston. So, that means, piston is given a finite value of velocity instantly. So, when such a things happens, we can say that whatever we discussed so far, that all there will be a series of waves that get generated subsequently. So, that means, an entire event, whatever small these small waves, now they keep generating in that small time instance. So, I can say that we will have a these pressure waves, we can have a first wave which is getting generated, this is the first wave and this is the nth wave, this is the last wave. So, there are n number of waves that tries to get generated. Now, with this n number of waves, if you look at the pressure in the medium, so pressure this region we have gas, stagnant gas, that is V is equal to 0, because the wave has not reached this region, and all these regions this gas has experienced the finite value of dV and it has seen the pressure P n. So, through this process I can say that we can say this pressure P n that gets generated with n number of waves, and if you say the first wave and this the nth wave, and this one we call as head of the wave, and this is what we say, that is last wave we say tail of the wave. So, that means, all subsequent wave number 2, 3, 4, likewise there are nth waves, and all subsequent waves will have speed higher than the first one. That means, nth wave will have speed obviously higher than the n minus 1th wave. So, likewise the event, when you look at this is one time instant we see t 1, when you see this event in the next time instant, we can see the same phenomena, sorry, first wave and nth wave, and they try to squeeze in a small region. I will say this as a delta x. Okay. So, this so entire pressure from P 0 to we say P n, that happens, change that happens in a very small thickness delta x, and we are looking this as at another time instance, maybe I say t is equal to t 2. So, with the lapse of time, all the compression wave generated will eventually try to overtake at some point downstream, and through this propagation of compression waves, the flow property information are shared. Now, as and when this compression waves moves into medium, the properties are shared. Shared, I mean that the pressure and temperature in the medium gets changed. So, this is how we see the sequence of event. So, in the sequence of event, when I say t is equal to t 1, t is equal to t 2, and I will say this t is equal to at one particular important situation t n, okay, where location x is equal to x n. So, here I say this finite length and delta x 1 and this say delta x 2 and we say here delta x tends to 0. So, what happens here when the all the waves, these waves number 1 and wave number n. So, eventually with respect to time and time t is equal to t n, what will happen, the nth wave will try to overtake. So, when the nth wave try to overtake, it means nth wave has merged with n minus 1th wave, then subsequent n minus 2 waves and finally second wave gets merged and finally and the end it will merge with the first wave. So, when such a things happens, it may happen that the nth wave will try to overtake. So, when it tries to overtake, we can represent such a phenomena as a dotted line. So, that nth wave try to overtake the first wave. So, that means that will be this wave is at the top and when this first wave is getting lagged. So, physically this what it means that in a given location of the flow field x n, we will have a different properties which is not true. So, if you look at this particular phenomenon physically, that does not true because at a given location and given time the gas has different values of properties. By mean different value properties means one property will have, the first wave will have given one assigned has one properties and nth wave will have another properties. So, this is not true or not physical in nature. So, such a event we will try to avoid such things because a natural occurring phenomena will give a solution to it as a merger of shock wave. So, this merger of shock wave and in this case it becomes a normal shock. So, it means it other word it means there is no compression of waves as such now. So, in these two situations there are infinite number of compression waves, but in this situation there is no compression waves because all these compression waves has merged to a shock wave. And since it is a one dimensional medium, we call this particular shock wave as a normal shock. Okay. So, this is how I try to explain this particular figure, and whatever has been written, we can say that at this stage when there is a normal shock is formed, its isentropic assumption is no longer valid. So, because viscous heat transfer effects cannot be neglected, the waves, all the waves will try to topple with one another. It means it will assign different values of flow properties at same time at a given location. So, which is absurd situation in the medium. Now, hence the compression waves tend to overtake. This phenomena may be viewed as a merger of all compression waves instantly at a given location and the process becomes infinitely steep. So, instead of the property change what that has happened supposed to happen gradual manner, this gradual manner has now becomes a, because this change happens in a very steep manner. That means, change is instantaneous and change the in a very small thickness domain. So, this is how we say a shock wave is formed, and the simplest form of a shock wave is a normal shock, but it is very strong. So, coming back to our physical phenomena, we say a natural occurring process will tell us that a merger of all compression waves will lead to a single wave at particular instant of time, and we call this as a shock wave. And physically it has a thickness of in the order of 10 to the power minus 7 meter, which is almost is very less. and mathematically it is represented as a this is instantaneous change or discontinuity in the medium with a limiting case when time tends to 0. So, now bringing all this mathematical and physical nature, we can now for our compressible flow field what we can say, the flow properties undergoes a finite change, there is a finite change obvious, but it is large across a shock wave in a non-isentropic manner. So, what we can view is a normal shock, the property change are finite, but very large. In for instance, what we can say that for a standing normal shock like this, if I assign the properties as P 1, T 1, rho 1, U 1, stagnation pressure P naught 1, stagnation temperature T naught 1, then what I am going to see. So, this is a given condition, what I am going to see is that pressure is going to shoot up, that means static pressure is tremendously high, total pressure will drop likewise, and Mach number will become all of a sudden subsonic. So, this says that this change takes place, and in this situation the process is happens in a non-isentropic manner, that means S 2 must be greater than S 1. If your entropy are calculated, we can say entropy is a it's a non-isentropic process, entropy is greater than S 1. So, as I discussed all these things, that the weakest compression wave is a sound wave, that is what in the beginning I said, that when you say instantly when you give a push to the piston, a sound wave is generated. Now, when that push was the push was given, the increment in the push is more and more, we try to increase more changes in the medium, and the initiation then and at one point of time it becomes a strongest compression wave, and that is a we call this as a shock wave. But since in a supersonic event, shock wave is a natural occurring process, but its initiation, that means when Mach number is just tries to become slightly higher than 1, it is seen as a Mach wave. So, Mach wave is initiation of the shock wave. Now, here we will talk about something on moving shock and stationary shock. I also viewed tell that a shock front can move also, or shock front can be, we can view it as a stagnant. So, in the first figure what we are seeing in a one dimensional medium consisting of large number of streamlines, we can see we are saying that a shock wave is moving, shock front is moving. Then when the shock front is moving, so your initial gas has no velocity here. So, when the shock front is moving, that is across the shock, we can say the across the shock the medium, that is we can say that when the shock front is moving in one direction, initial condition of the medium is P 1 rho 1 T 1, and final condition of the medium is P 2 rho 2 T 2. And as I said, since in this medium the shock wave has not crossed, so we say ahead of the shock, and in this case the shock wave has already crossed, so we say behind the shock. So, likewise the similar way we can say pressure P, initial pressure let us say P 1, and initial pressure it becomes P 2. So, this is how we view that property change across the shock wave. Now, in this case the shock wave has not crossed, so gas velocity u is equal to 0, and here it has a finite value of u. So, this is a scenario when we have a moving shock. Okay. Now, in the same scenario we bring the arrest the shock stationary. Let us say that we say it is a stationary medium. So, why we do this? Because let us say if at all we want to come across similar pressure change across a normal shock, what we do is here is arrest the shock to stationary. So, that means there is no shock velocity, you allow the gas to pass through the shock wave. So, in other words what we are trying to say, to come across, so other words what we are trying to say, to come across similar jump what that we had in the moving shock, if we want to have in the same change in the stationary shock, then what would have been our scenario. So, here the terminology that we use as a before the shock and after the shock. So, before the shock our case condition was this P 1 rho 1 T 1, but we allow the gas to move at E 1 and finally, we arrive this final velocity of the gas U 2. So, this corresponds to a Mach number m 1 and this corresponds to a Mach number m 2. So, this is the after the shock. Now, if same thing if you want to see here, the pressure signal change will remain the same, but what changes is the gas velocity. So, here what we have to do is, since it is a relative velocity we are looking here in a laboratory frame for a moving shock, but when we are looking in the laboratory form as a stationary shock, what you see here is gas is moving. So, your initial velocity will now become u 1, which is this one, that corresponds to Mach number m 1, and the final velocity is u 2. This is how the change that happens here. So, in our concept, in our scenario, we will only talk about a stationary shock situations and we will try to see what are the conditions before the shock and after the shock. So, this particular correlation was done, that in many practical problems we will try to see that moving shock situations, but if you can bring them to a stationary shock situations, the analysis will become simpler. So, that is what this judgment is made, that a moving shock analysis, how it is framed to a stationary shock reference and with that respect how the change is going to happen. So, with this logic we will move further only towards the stationary shock analysis. Okay. To have this stationary shock analysis, we will now talk about some fundamental equations of normal shock, that we the similar way what we did earlier for an isentropic flow in a one dimensional medium. So, what we say, a normal shock is the one in which properties change drastically in one direction. So, here we view this normal shock wave as a stream tube, as I mentioned, it is a imaginary duct. We can assume to be a one dimensional duct, which is there is imaginary duct, which means that as if there is no boundary, although there is no physical boundary, but we can assume to be a imaginary boundary that enclose this normal shock, and the streamlines that comes they are perpendicular to this shock wave. So, obviously, we call this as a stream tube and the streamlines are parallel to each other, but they are normal to the shock wave. And this analysis was considered in one dimensional flow framework with constant cross sectional area. Another kind of assumption that we make is that since we say it is there is no boundaries, there is no physical boundaries. So, it is imaginary duct. So, we can another assumption we can make, there is no frictional effect because shear stress are absent and there is no boundary layer, and the configuration of the duct can be treated as a constant area duct. The shock thickness is very small compared to the dimension of the stream tube. That means, shock thickness is very small with respect to stream tube dimension. Okay. And the flow process includes to be adiabatic. That means, if you say there is it is imaginary duct, there is no heat addition into the duct. and the flow process in the shock wave is assumed to be steady, there is a steady flow, and the all the properties conditions in the region 1 and region 2 needs to be mapped. So, basically this is the given problem that if we have a standing normal shock and before the shock we have the given conditions of static pressure and static conditions and stagnation conditions, flow velocity. These are the given conditions, and we are supposed to find out the unknown conditions, that what happens after the shock. So, after the end of the analysis we will try to see that what is the relation between the static to static pressure to static temperature ratio, static pressure to static pressure ratio before the shock and after the shock, static temperature ratio before the shock and after the shocks, and that we are trying to correlate with the information in the velocity or flow Mach number, that is before the shock and after the shock. So, this is the entire philosophy of our study, and finally, we will use the same one dimensional framework equations, that is continuity equation P rho 1 E 1 is equal to rho 2 U 2, momentum equation P 1 plus rho 1 E 1 square is equal to P 2 rho 2 U 2 square, and it since it is a constant area. So, there is no area term here in this equation, and in fact, for the energy equation we use the same equation what we did for isentropic flow, that is total temperature before the total temperature for region 1 and region 2, and here we have to assume that is Q to be 0, because it is an adiabatic duct. But here our philosophy is that we do not know the conditions P 2. Okay, you do not know the conditions P 2, but we also do not know the what are the conditions in the M 2. In isentropic flow with known Mach number, we can correlate the property information at different locations in the flow plane. So, there is no, it is adiabatic situation, there is no heat addition, and apart from this we will use these other relations, that is P is equal to rho R T, H is equal to Cp times T. This is the gas, this is the calorically perfect gas, this is the ideal gas equations, and also use this term S square is equal to gamma R T or gamma P by rho. So, this is the speed of sound. Obviously, speed of sound is very important here, because the Mach number is going to change, and in fact, except this domain we have to say, except this thin shock wave region, all the flow fields are isentropic except this thin region in the shock wave. So, with this we will conclude for this lecture today. Thank you for your attention.